till now, we've been able to understand how pure states change in time in quantum mechanics by using the time-dependent Schrödinger equation. With a mixed state, we could continue to do that. We would use Schrödinger's time-dependent equation to tell us how any specific pure state would evolve in time. Then we would use our presumed probability distribution over all those pure states and appropriately average the answers. The density matrix can offer us a much more convenient way to write this, however. So let's see how this is done. We can directly calculate the time evolution of the density matrix. We start with the Schrödinger equation for any particular one of the pure states in our mixed state. So for example, for some specific pure state psi j, here's our Schrödinger equation as usual, and we can substitute using our expansion of this pure state in our basis of interest here. And that will give us a rewrite of this equation that will look like this. Here, all the time dependence of the state is in these coefficients here. Now, operating from the left with a specific one of the basis functions on the expressions that we just had, we'll obtain the following. And we can, of course, rewrite this because this phi m and phi n here will mean we pull out just one term from this sum, the one with m equals n. And on the right-hand side, we can merely move the phi in here. This is just a number after all, so we can move the phi in here. And of course, that just gives us this matrix element here. We can take the complex conjugate of both sides of this expression here, noting that H itself is Hermitian. That means the matrix elements obey this relation, that H star Mn is the same as H n m. We have this version, the complex conjugate of this leads to all of this here. Or trivially changing indices, which will be more convenient later on, we'll talk about Cn here, and we'll sum perhaps over some index S instead. So we're just changing indices, there's no change in the physics. It will be more convenient later on not to be summing over n here, so we'll have some other index. But from our previous result for the elements of the density matrix, so here were our density matrix elements, we can take the time derivative to obtain this kind of expression. So we have to take the time derivative of the product of two functions of time, and of course that gives us this kind of form when we take the derivative of a product. Now we can substitute using our previous results for these kinds of terms. So here we have this one, which is going to be like this one here, and this one, which is going to be like this one here. Note that we have changed our summation index to Q in the first of these results here. We're using Q in here. Hence, this expression becomes the following expression. As I said, we changed the index to Q here. And we can regroup the terms here, moving the sums around, moving this sum over J inside the sum over Q, and similarly inside the sum over S. Note that by definition, of course, this element of the density matrix is just this expression, so we recognize these kinds of elements appearing in here. So we can substitute for these terms based on density matrix elements. And specifically then, using that substitution, here are our density matrix elements. This is here the mnth element of the product of rho and H. So we're summing over Q in a matrix product as usual, and this is the mnth element of the product of H and rho. Summing over S in here in the usual matrix product fashion. And so what we have here is that d rho mn by dt, partial derivative, is I over h bar times the mnth element of the commutator of rho and h. And since this is true for every matrix element Mn, we therefore have this expression. The partial derivative of the density matrix or operator with respect to time is I over h bar times the commutator of the density matrix or operator and the Hamiltonian, which tells us how the mixed state evolves in time. And this is a key result for the density matrix.
So, now we've managed to come up with quite a simple equation for how the density matrix evolves in time. Remember, we've actually added nothing so far into the physics. We could get exactly the same results from working with the time-dependent Schrödinger equation separately for each of the pure states in our mixed state, and then finding the ensemble average results at the end. Incidentally, for a pure state, this expression for the time evolution of the density matrix is exactly equivalent to the time-dependent Schrödinger equation. Hence, this formalism with the density matrix is universal. It will work for pure states just as before, but it can also handle mixed states. This is one reason why the density matrix notation is heavily used. But there are things we can add to the density matrix formalism that make it even more useful, and that will be the subject of our next section.